So any polynomial in T2 can be written as a linear combination of these basis elements. So we want to find the matrix TB. Remember, this would have been TB prime, but since it is a linear operator, it is TB of this with respect to the basis element. So we use it to compute that. You see, once you have a matrix of transformation, then to compute that, you simply need to get this matrix times here you remove you write this as a linear combination of the basis here, then you get the PB, then you multiply it here to get, okay, so this is what I'm saying, that the polynomial P of X, it is that, this is the definition we are given. So T of 1, it will return 1. Then T of X will be 3x plus 1 and x squared. So this is, we are transforming the basis elements. In other words, that one will give us this. So we can write this now, which is in the image space, as a linear combination of the basis elements. I said where we have -2, it is supposed to be 1. This is an error. Where we have -2, it is supposed to be 1. So this is an error. So we write this as a linear combination. We can write 1 as 1 times 1, then 0 times x, then 0 times x squared. So that one gives us this. So this one becomes a column in the matrix of, in the transformation matrix that we are looking for. So with T of x is 3x minus 5, but we can write this as minus 5 times 1 plus 3 times x plus 0. So that one also gives us its basis as minus 5, then 3, and 0. Likewise, T of x squared, it can be written as this, as a linear combination, so it gives us that. So we have this matrix TB as that. Then, to find this image, we need to get the matrix of transformation times the vector corresponding to this element here. So when we write this element as a linear combination of the basis elements, then we see that the vector we are looking at is going to be, okay, so we transform, here we are transforming the coefficients, so it will give us 1, 2, 3, 1, 2, 3. So when we substitute, look at this equation, so when we multiply here, this should have been T of B times this, okay, what I have here, it should have been this. There are so many typos I need to work on, so it should have been this. That's what should have been here. So when I multiply, I get this. So it means these will be the coefficients of the image of this, and it will give me that. But the question was also asking us to compute this directly. How do we compute this directly? The transformation says where there is x, we put 3x minus 5. So when we do that and expand, it takes us here and it takes us here. So we see that when we compute it directly, we get the same result like when we use the matrix of general linear transformation. We get the same result like when we use the matrix of general linear transformation. So James, does that answer your question, sir?
Have you seen that? Yeah, I hope you have seen. So that's where it comes from. Now here we have a summary, Jean and Bashir. This summary is that
James, does that answer your question?
Description, when you want to describe the state of the system using the quantum
James,
approach,
unmute your microphone and talk to me.
You get the possible energy state.
Okay, any other question, please, before I take you to example 2?
Or you baptize them names. Like you can say R1, R2.
I feel it is okay, sir.
Now,
Okay. So let's proceed to example 2. In example 2, we have still a linear operator taking things from R3 to R3. And this linear operator, it is just defined by when you give it an X, it returns an X. So it looks like the identity operator, it changes nothing. Whatever you give it is what it returns. So the basis for R3, we have different bases for R3. So the first R3 B1, which is the basis of the domain space. Then B2 is the basis for the codomain space. So we want to find the matrix representation of T, which is B1, B2 now. So this is what we do. We transform the basis elements. So we write the T of 1, 0, 0, it returns 1, 0, 0, because that's what the vector does. Whatever you give it is what it returns. Now we write 1, 0, 0 as a linear combination of the basis element B2. So it will be 1 times this, 0 times 0 times. So you see, this gives you 1. Plus 0 plus 0, so it gives you this 1. This is 0 plus 0 plus 0, so you get this 0. Then lastly, this is a 0,
yes, it is
a 0 plus a 0, which gives you that 0. Okay, so that means that T2, this is the second basis element, 0, 1. It also gives the same element, and then we write it like this as a linear combination. We want to have a 1 here, so we can have this as negative 1 and then 1, such that the one in the middle will be 0,
the quantum numbers
minus 1, then plus 1. This one will give us a 0. This one is for this. I'm sorry, there is a way this is disorganized. I think I can put it right. Give me 2 minutes. I first put this right, then I come back and I explain it better. This one is a bit disorganized. But after that, this is the exercise we work on. So let me change something little and I come back.
Are you there, Jean? Okay, you are there. Now we are on lecture 4, and in this case, we are coming to what we call an ensemble. Are you there, Jean? Okay, an ensemble. What is an ensemble? An ensemble, it is simply a collection of elements of uniform or of similar characteristics. For example, if I go to a physics class, whereby all of you do physics, you can be taken to be an ensemble. Reason being, one of your major characteristics you have there is that all of you do physics. So a collection of elements of similar characteristics is defined to be an ensemble. So that is the definition of an ensemble in brief. So in this, an ensemble may contain a few or many or infinite members. In other words, it may have few members, it may have a number of them, not very few, or it may have uncountable, that is infinite. As simple as that. Now, let us come to the assumption of statistical mechanics. There are 3, and I want you to master them at least today, because at least you must be memorizing something before we end this lecture, something that you tell your neighbor when you get out. One of the assumptions is that an isolated system in equilibrium is equal likely to be the n of the accessible state. What is an isolated system? That system which can stay independent. It means an isolated. Okay? If it can stand on its own, it is defined to be an isolated. And so long as it is in equilibrium, it is the same. By the way, this thing can be practical. For example, you go for a party.
So the
When you
T,
go for a party, all of you who have gone for a party, you are equal.
so
There
the
is no
T
minister, there is no church priest. All of you are ordinary people of the village. That means you are in equilibrium. Each of you are equal. So in this case, anybody can sit anywhere. One can sit in front, one can sit behind,
Hello.
something like that. So
Hey, kuniona
in this way,
okay, let me check it.
we have it as that an isolated system in equilibrium is equally likely to be in any of the accessible state. That's one. The second one is that the equilibrium state of the system corresponds to the macro state of the maximum probability. The equilibrium state. The equilibrium state of the system corresponds to the macro state of maximum probability. What does it mean to you, class? That when we are taking an equilibrium state, it should be that state for a larger system. Because when we talk of macro, it is for a larger coverage. You know, there is what we call micro and macro. Macro large, micro small. So when we say that that second assumption is that the equilibrium state of the system corresponds to the macro state of maximum probability, that's what it means. That this equilibrium state, it is that one of a larger coverage for this given system, but that one that appears many times, that gives the equilibrium state. Then the third one is very simple, that the number of particles of the system are constant. As simple as that. So those are three. Now, that one must have brought us, when you go back to your notes, now we're on page 38. I don't see here those assumptions of statistical mechanics, but we are going to find them in front. Only that I wanted to bring them here because we are just starting this statistical ensemble. Now, here we are having our diagram, which has M, V, E, and those are just physical properties of the particles within an ensemble. So we are using them to define what an ensemble is. Now you find that as we are going to see, as we are going on, we are going to find that these ensembles, they can be classified into three. One is called microcanonical ensemble. The second is called the canonical ensemble. Then the third one is called the grand canonical ensemble. So class, you'll find that these properties of these different ensembles will be different. Now,
are we going
the one whereby
sorry,
the number of particles, the volume, the energy.
Are we going? Oh,
yeah. I'm rectifying something in my codes, and then I come back.
What we call the
Okay.
canonical ensemble. Jean, are you hearing what I'm saying?
To end, yeah.
I beg your pardon? Okay. Okay, now I think we are going to break it from there. If you have any question now, you can raise it. We are going to stop it from there. Is there any question? Any question, class? Okay, have a nice day, sir. Have a nice day. Eh? Okay. Okay.
Okay, hope you're still on. I'm done with what I was rectifying, so I can take you through this example 3, and then we should be able to end the lecture there. Are you still around?
Yes.
Okay, so in example 3, we want to look at a transformation T which takes things from R3 to R3. And this is its definition. It's an ident transformation. When you give it X, it returns X. Whatever you give it is what it returns. R3, these are the two different bases for R3. This is the basis, the basis. So this is the basis of this domain space. This is the basis for this codomain space. So we want to find the matrix representation of this transformation T. So we transform the basis elements. That's what we do. So the T of this first basis element, it returns the same, because this is how the transformation is defined. Give it an X, it returns an X. So T of this, it returns that. So what do we do after this? We write this as a linear combination of B2. So we write it as a linear combination. So to get this, we need the 1 here, a 0, 0. So we can get this times 1, then 0. This one is the first basis element in B2. This is the second basis element in B2, third basis element in B3 rather, B2, basis B2. So this is 1, then 0, 0. So it returns that. So this is we find the image of this, it is that, and we can write it. So there is an equal signs again here. I'm supposed to put equal signs here. So that one, since we want a 0 first, so we can put -1 here, 1 here, 1, such that this will be -1 plus 1, which gives us this first 0. Then this is 0 plus 1 plus 0, so which gives us that. So this is the only way we can get that. So the image of the third basis element in B1, it is this in B2. So write it as a linear combination to get that. So the matrix representation is the column for this, column for this, column for that. So what is the column for this? What is the column for this? It is 1, 0, 0, which is this. What is the column for this? It is -1, 1, 0, which is this. Then lastly, we have 0, -1, and 1. So it takes us here. So this is the matrix representation. That one is the matrix representation. Okay, so I am done with this example. Now I need questions. Then after questions, there's an exercise for you, and then we end there. Questions?
That example is clear for me.
Okay, okay. Others, are you
Me
okay?
too.
Okay, fine. So you will take time and work out this example. Remember, there is some work from previous lecture, and now this is also work. Next time we meet, if time allows, then anyone who is ready to present can make a presentation. So in the first example, it is a linear operator.
Okay, sir.
The second one is a linear transformation. It maps R3 to R2. The third one, this Pn is a general polynomial. So you use knowledge of example 2. In example 2, we dealt with a polynomial of degree less or equal to 2, but now this is a polynomial of degree less or equal to n. So you use that knowledge. Then the knowledge of example 3 applies here in number 2, then the knowledge of example. You see we have 3 examples and 3 exercises, and each exercise corresponds to the example. Okay, so I want to take a break of 5 minutes, then we meet for the other lecture. Is that okay?
Okay, thank you.
It's
Yeah.
okay, but sir, how can I access these notes, please? Because me, I can't see it on the platform. I see the other odd thing.
What
I
is
don't
your
know whether
name?
it's the system name not
What is your name?
Katongole James.
Katongole James. Okay.
Katongole James.
Yeah, let me work
Yes.
on you. Let me work on you right now, and then you look for all linear algebras where you're enrolled. There are 2 courses on the system. Of course, at first they had given this course an error for a 3rd year course, but they rectified the error. That's why the system has 2 courses. So one has notes, the other one doesn't have notes. So I'm going to enroll you in the one with notes, and I have even posted its picture on WhatsApp. Make sure you look for it, and then you access the notes. I would have sent the notes. I would have sent the notes on email, but it's not helpful because we will do our assignments and tests from the platform. So it's better you get them from the platform. Okay. Any other question?